Why your TV is never actually OFF, the hidden invoice. Look closely at this image. What you are seeing is a thermal camera view of a standard living room at 3 a.m. The room is dark. The air is cool. The occupants are asleep. But look at the entertainment center. The set-top box and the bottom chassis of the smart TV are glowing a bright, angry orange. They are radiating heat. They are reaching temperatures of 40 degrees Celsius. This footage was taken 6 hours after the owner pressed the power off button. You pressed the button. You saw the red light appear. You assumed the transaction was over. But mechanically, nothing stopped. The engine inside that plastic box is still running. It is still processing data. It is still talking to servers. And most importantly, it is still billing you. This is not a malfunction. This is not a defect. This is a feature you paid for. It is called active standby. And right now, you are paying a monthly subscription fee for a service you didn't know you had. Myth busting. To understand why your off button is a lie, we have to unlearn what a television is. 20 years ago, a TV was a dumb appliance. When you flipped the switch on a CRT television, you physically broke the electrical circuit. A piece of metal separated from another piece of metal. The flow of electrons stopped completely. 0 watts. 0 activity. Today, your TV is not a TV. It is a computer attached to a large display panel. Your set-top box is not a tuner. It is a high-performance server running a complex operating system like Linux or Android. And here is the fundamental truth of modern computing. Computers hate being turned off. Think about your laptop. When you shut it down completely, what engineers call a cold boot, it takes time to wake up. It has to load the kernel. It has to initialize the drivers. It has to handshake with the network. It has to verify permissions. This process takes time. Maybe 40 seconds. Maybe 2 minutes. But you are impatient. Consumer psychology data shows that if a TV takes more than 7 seconds to turn on, the user perceives it as broken. You demand instant on. So, manufacturers made a choice. They removed the off function. They replaced it with a simulation of off. When you press the power button now, you are merely sending a software command to cut the video signal to the HDMI port. The screen goes dark, but the brain remains wide awake. Mechanism, deep dive. Let's dissect the engineering behind this phenomenon. We need to look at 3 specific systems: the boot architecture, the power physics, and the network chatter. First, let's look at the architecture. Engineers call this state S09, or modern standby. To give you that instant startup, the RAM must stay fully powered to hold the operating system in memory. The CPU must stay in a low power state, but it must remain active to process background tasks. If the device truly turned off, it would drop the IP address from your router. It would lose its place in the network. So, it stays in networked standby. It is like a car idling in your driveway 24 hours a day, just so you don't have to turn the key. The car isn't moving, but the engine is hot, and the gas tank is draining. Second, let's look at the physics of that heat. Why does a device that is doing nothing generate so much heat? This brings us to this switched mode power supply, or SMPS. Your wall outlet provides 110 or 220 volts of alternating current. The chips inside your box need 5 volts or 12 volts of direct current. The SMPS handles this conversion. Here is the engineering constraint. Power supplies are designed to be efficient at specific loads. They are usually most efficient when the device is working hard, at 50% to 80% capacity. At this sweet spot, most of the energy becomes computing power. But when the device is in standby, the load drops to the bottom of the chart. You might think low load means low consumption. Mechanically, yes. But efficiently? Absolutely not. At very low loads, the efficiency of the power converter crashes. The internal transformers still suffer from core loss. The switching transistors still have to switch thousands of times per second. Because the load is so low, a huge percentage of the energy drawn from the wall is not used for computing. It is wasted. Physics demands that this wasted energy go somewhere. It cannot disappear. So it turns into heat. That heat you feel on the top of your set-top box is not processing power. It is the physical manifestation of electrical inefficiency. It is the sound of your money burning off into the atmosphere. Third, let's look at the network. Even if you don't care about the heat, you should care about the data. Your devices are legally obligated to talk to their masters. We call this the keep alive signal. While you are sleeping, your off device is performing multiple tasks. It is downloading the electronic program guide for the next 7 days. It is performing a DRM handshake to verify your subscription rights. It is broadcasting its presence to your router via ARP packets. It is reporting usage analytics back to the manufacturer. To do all of this, the Wi-Fi or Ethernet chip must be fully powered. The processor must analyze the incoming packets. The storage drive must write the data. You think the room is silent. But on the radio frequency spectrum, your living room is screaming. The invoice, so what does this actually cost? We are not talking about the 0.5 watt passive standby that regulations talk about. That is for devices that truly sleep. We are talking about active standby. A typical cable set-top box in active standby draws between 15 to 30 watts. Some older models draw almost the same power off as they do on. Let's be conservative and say 20 watts. And let's say you watch TV for 4 hours a day. That means for 20 hours a day, the box is in active standby. 20 watts times 20 hours equals 400 watt-hours per day. That is 146 kilowatt-hours per year. For one box. If you have a second box in the bedroom, double it. Now add the smart TV, which often draws 15 watts just to listen for your voice command. In a typical household, you are looking at roughly 400 to 500 kilowatt-hours per year consumed while the screens are black. Depending on your local electricity rates, that is $50 to $150 a year. Not once. Every single year. Over the 10-year life of these devices, you are paying $500 to $1,500. That is enough to buy a brand new 65-inch 4K TV. You are effectively buying a new TV every decade, but you never get to see it. You just feed it to the power company. Utility protocol, so is it worth it? You have a choice to make between convenience and cost. If you decide that this phantom invoice is too high, here is how you can change the equation. Step 1. The kill switch implementation. Do not rely on the remote control. Connect your entire entertainment center, TV, box, soundbar, to a master power strip with a physical switch. When you are done watching for the night, flip the switch. This forces a mechanical G3 disconnect. Consumption drops to absolute zero. The heat stops immediately. Step 2. Disable quick start modes. If you cannot use a power strip, dig into your settings. On your smart TV, look for settings labeled Quick Start, Instant On, or Networked Standby. Turn them OFF. Select Eco Mode or Energy Saving Mode. This tells the computer to actually shut down. Yes, You will wait 30 seconds for it to boot up next time. That is the price of savings. Step 3. Audit the ghost boxes. Identify devices you rarely use. That old DVD player? The gaming console you play once a month? These are likely drawing power 24/7 just to light up a tiny red LED. Unplug them completely. Only plug them in when you intend to use them. Conclusion: the engineers who designed this system were not evil. They were solving a problem. The problem was you. They knew you hated waiting. So they traded efficiency for speed. They traded your money for your user experience. It is a valid transaction, but it should be a transparent one. Now you know the cost of that red light. The next time you walk past your dark living room, remember, the red light isn't a warning. It's a receipt.